Hello, and welcome back to the lab. On the bench today, we have two pieces of Hewlett-Packard test equipment. On the right, we have the HP200CD, which we have featured in previous videos on this channel. And on the left, we have the HP204C. Both of these are examples of Wien bridge oscillators. The 200CD is a tube-based oscillator, and the 204C is a all-transistorized solid-state version of the same oscillator. Both of these are examples of Wien bridge oscillator circuits. So today I thought we would talk about the Wien bridge oscillator. First, we'll take a look at the basic circuit of a Wien bridge oscillator. We'll compare and contrast the differences between the circuits of these two instruments. And then I thought maybe we would try to build our own Wien bridge oscillator using an op amp and a light bulb, something I've never tried before, but I thought it might be fun. So let's go. So first, let's take a look at the basic circuit of the Wien bridge oscillator. First off, I am sure that in actuality it's pronounced Wien, not Wien. It's pronounced Wien, like the city in Austria, right? But everyone I know has always called it a Wien bridge, and including myself. So I'm going to call it the Wien bridge oscillator. Um, so the Wien bridge oscillator consists of an amplifier and a Wien bridge, which is two legs of a bridge. Um, these two legs provide both positive and negative feedback to the oscillator. Um, the positive feedback sustains oscillation, and the negative feedback provides amplitude, stability, and automatic amplitude control, as well as minimizing distortion levels of the output. So you have a pure sine wave at the output. In the positive feedback leg of the Wien bridge, we have a series RC circuit and a parallel RC circuit. The series RC circuit effectively is a high-pass filter, right? And the parallel RC circuit is effectively a low-pass filter. And where those two frequencies uh, intersect, that is the main frequency that passes through and provides positive feedback to sustain oscillation in the amplifier. And that gives us our basic oscillation. Now, in order to prevent the oscillation from running away completely, we have to stabilize the oscillation with some negative feedback. That is done with this half of the Wien bridge. What happens here is we sense a little bit of the output through this resistor and an incandescent light bulb. This becomes the other half of this resistive voltage divider, okay? And what happens with the incandescent light bulb is its resistance varies with temperature. And of course, its temperature varies with the amount of voltage applied to it. So therefore, its resistance varies with in inverse proportion to the amount of voltage applied to it in some fashion. It may not be directly linearly inverse, but in some fashion, it responds to the level amplitude of the signal applied to it and changes its resistance accordingly. Specifically, as it heats up, its resistance increases. If the resistance increases, the amplitude at the level at this point, this node will also increase because of the resistive voltage divider in this leg of the Wien bridge. That increases the amount of negative feedback in the amplifier and reduces the output of the amplifier, thus automatically stabilizing both the amplitude and the amount of distortion in the amplifier. Without this leg of the Wien bridge, you would have a square wave at the output. It would just simply swing to both power supply rails during its oscillation. But with the amplitude and distortion control of the negative feedback leg of the Wien bridge, what we have is a pure sine wave at the output. It minimizes distortion, maximizes amplitude stability as you change frequency. Now, the response of the light bulb is such that it doesn't respond to individual peaks of the waveform at the output. It responds more slowly than that. effectively being an envelope detector so that it responds to the slow overall changes in amplitude of the output signal. Um, in response to that, it will vary its resistance such that it basically maintains a constant amplitude at the output as you change frequency. It also minimizes the distortion of the output. When this resistor is adjusted to properly give the proper amount of negative feedback, the light bulb responds automatically to that signal problem, that signal error. Now, in most circuits, the C is the same and the R is the same, and the frequency is determined by 1 over 2 pi F, or 1 over 2 pi R times C. So if you have C's equal and R's equal, then here's the frequency that the positive feedback will resonate at and provide the oscillating frequency. Um, in order to have a variable frequency, you can either adjust the resistance or adjust the capacitance. In both of these Hewlett-Packard instruments, they adjust the capacitor because it seems to be uh, easier to have capacitors which track one another when they are ganged together. So as you increase this capacitor, this one increases by exactly the same amount, and that's how you vary the frequency of the oscillator. This circuit is precisely what is used in the HP200CD, the tube oscillator. It uses a light bulb as the amplitude envelope detector, amplitude sensing element, and automatically changes its own internal resistance to uh, compensate for changes in the output amplitude, um, making it automatically uh, reduce its gain or increase its gain as necessary to sustain oscillation and yet not provide any harmonics. So you have a pure sine wave at the output. Now here's the circuit that the HP204C, the solid state version of my oscillators, of my Wien bridge oscillators, uh, this is how this one works. It's the same basic circuit. We have a positive feedback leg and a negative feedback leg in the Wien bridge, okay? But instead of using a light bulb as the amplitude controlling resistor here, in the negative feedback leg, what we do is we have a basically a diode detector that detects the amplitude envelope like an AM demodulator, essentially. Um, we smooth that out through an RC filter, um, and then we use that voltage to control a FET, which uh, the resistance through the FET varies according to the voltage on the gate of the FET, thereby providing the feedback. So the 204C solid state oscillator does not use a light bulb. It uses this more complicated um, feedback circuit, and there's some other additional circuitry in here, buffers and so on and so forth, and voltage level shifters to make the FET bias properly and so on. But essentially, it's the same basic circuit, except they have replaced the light bulb with a FET and some control circuitry to drive that. So this is the Wien bridge type oscillator circuit in the 204C. So let's take a look at the actual schematics of these two instruments and compare them. Okay, so here's the 200 CD schematic, the tube-based oscillator, Wien bridge oscillator. Um, of course, there are no op-amps in the 200 CD. They're all tubes. And we have a balanced circuit. So it's a balanced amplifier circuit that uses a push-pull output stage. Um, Actually, these are emitter follower, cathode followers, and they drive an output transformer. There are two different output transformers, one for the low frequency ranges, and one for the high frequency ranges that connect to your output. Um, but it's a balanced amplifier circuit. So the positive and negative feedback comes through in this manner. Here's the Wien bridge part of the circuit. You can see here is the series resistance and capacitance in the series part of that positive feedback leg. Here is the parallel resistor and capacitor combination in the negative, also in the positive part of the feedback leg. You'll see in the 200 CD that there are actually two sets of capacitors, tuning capacitors in parallel with one another in this series leg, and only one capacitor in the parallel leg. But the resistors are opposite. So this is half the value, and this is twice the value. So the combination of R, 1/2 R times 2C is the same as the combination of R times C. So this is essentially the same, except that actually uses 3 capacitor gangs. 2 of these are in parallel with one another, so they add their frequency. And this one, they add their capacitance. And this one is just a single third gang of the tuning capacitor. So that provides your positive feedback, and the negative feedback is provided to the grid of this amplifier tube, and that is adjusted with this variable potentiometer here. And here is the light bulb circuit that we talked about before. A very ingenious way of providing automatic gain control, amplitude control, and minimizing distortion, simply by automatically adjusting the resistance of the light bulb because of the temperature of the light bulb, which is because of the amplitude of the signal applied to it. That automatically adjusts the amount of negative feedback into the amplifier circuit. So that's how the 200 CD works. Let's take a look at the 204C. Okay, here's the schematic of the 204C. Now, of course, there's no twos, but there's also no op amps, no chips in this instrument. It uses a FET on its input for high impedance input, and a series of transistors to do the amplification. We have a totem pole output stage here, basically emitter followers, the same as the cathode followers in the 200 CD. Okay, we have positive feedback through that one leg of the Wien bridge. Here we have the series leg of the Wien bridge with one tuning capacitor and a fixed resistor for each range of frequency. And here we have the parallel leg of the tuning of the Wien bridge, where here's the tuning capacitor in parallel with a fixed resistor. The 204C does not use 3 gangs of tuning capacitor. It only uses 2 gangs of tuning capacitor. So the value of this capacitance is exactly the same as the value of this capacitance, which implies that the value of this resistance should be exactly the same as the value of this resistance. And in fact, it is for each frequency range. FET at the input, which provides high impedance like the gate of a tube. So that's how your amplifier works. This is your positive feedback to sustain oscillation. The negative feedback, instead of going to a light bulb, it goes through a bunch of circuitry, which provides some level shifting, and basically a diode detector here provides a time constant and a resistance, a time constant that's selectable depending on range, so that you can track the envelope of the amplitude without tracking individual cycles. That voltage is applied to the gate of this feedback FET Q2, which takes the place of the light bulb in the 200 CD basic oscillator circuit. So it's a far more complicated circuit. To replace the light bulb, they use a FET and a bunch of other envelope detection circuitry and some low pass filtering so that we can provide the negative feedback for amplitude control as well as minimizing distortion. There's an output attenuator and so on and so forth. So that's the 204C circuit. Now, I thought I might try to build an op-amp based circuit using a light bulb. So let's see how we did with that. Okay, so again, this is the circuit we're trying to build. And I don't have variable capacitors or variable resistors that are ganged. So I'm just going to use a fixed C and a fixed R. And I actually chose 10 nanofarads for C and 10 kiloohms for R. And when you put those values into the formula, you get a frequency of something like 1.5 kilohertz. Okay, so that's the frequency that this thing should oscillate at. I just picked an op amp out of my parts bin. I put a trimmer resistor in here so I can adjust the value of this resistance to provide the correct amount of feedback. I had a light bulb. I don't even know what kind of light bulb it is, but it's a light bulb that I bought, and I actually purchased the wrong light bulb by mistake. It happens to be a 6-volt light bulb. Okay, I can tell you that much, but I don't know anything more about it than that. The power supply rails on the op amp are plus and minus 6 volts. So the light bulb probably should not light because it's not going to receive the full amplitude, the full amount of power. So hopefully we can get this circuit working properly and adjust the value of this resistance so that we can get a pure sine wave at the output and at this resonant frequency of 1.5 kilohertz. So let's see the circuit that I built and go through it. Okay, very, very simple. It's exactly the same circuit that we just looked at. I didn't add anything extra. I have a series and parallel RC combination, 10 nanofarads, 10 kiloohms. Here's my resistor, this variable trimmer resistor. There's the light bulb. You might not even be able to see it, but the light bulb is right there. Okay, I stuffed it in there along with an op amp and my scope hooked up to the output, and let's turn it on and see what we get. All right, look at that. It looks like a sine wave to me. How about that? You can adjust this little trimmer resistor. You see if I can do that here. As you decrease the resistance, the amplitude, the amount of negative feedback increases, which decreases your amplitude until you have so much negative feedback that it stops oscillating altogether, like right here. And now I dial it down, and if I reduce the amount of negative feedback, we will start to get clipping as the oscillator swings to both supply rails, positive and negative. Somewhere in between those two extremes, we will have a nice clean sine wave with minimum distortion. Now, of course, I can't vary the frequency of this particular oscillator because I have fixed R's and C's, but it should be at about 1.5 kilohertz according to the calculation. I'd like to hook it up to my spectrum analyzer and see what it looks like in the frequency domain. Take a look and see what kind of harmonics are coming out of it. We can also measure the frequency more precisely that way. So let's do that. Okay, so here we are hooked up to the input of the 3585A spectrum analyzer. It looks pretty good. Let's put the marker down on the fundamental here and see what we have. Turn the frequency counter on. 1.534 kilohertz. That's just what we calculated, 1.5 kilohertz. Very good, very good. Let's do an offset 0 off. We can do a relative measurement. And our second harmonic, negative 50.7. Very good. Third harmonic, negative 58.5. Very good. Very good. I am very impressed. I didn't know if this Wien Bridge oscillator circuit was actually going to work or not, but it looks like it's working great to me. I bet I can probably get that distortion even a little bit lower if I play with that trimmer resistor a little bit. But it looks pretty good just the way it is. All right, so there it is, the Wien Bridge oscillator. Thank you very much for watching. Please subscribe and like this video and come back to see more. Thanks again.